We're going to take a look at an example that actually has 5 variables here, and so immediately we can conclude that it's going to be pretty difficult to get any sort of visualization in this data as a whole. Specifically, we can't visualize calorie, sugar, fiber, protein, and sodium at the same time. We can, of course, plot, calories versus sugar and have a graph and then plot some pairs or calorie, sugar, and fiber, but we can't visualize all 5 of those at the same time. And as you can see here, we have all of these cereals, and to kind of make sense of this is going to be a little bit difficult, right? Now, fortunately, in this given example, we do have some intuition. Like, for instance, we would, maybe expect some of the sugary cereals to, be higher calorie or at least, maybe a little less healthy, I guess. So like cinnamon swirls, we see, that has a higher sugar content, as well as Cocoa Puffs. And we can also see that they have relatively lower fiber than some of the other ones that don't have as much sugar, right? We can see like Proteinos, they have a lot more fiber than cinnamon swirls or Cocoa Puffs. Also, we see maybe that the sodium is a little bit higher in some of those, although that's not really consistent because the Fiber Crunch has a lot more sodium. So we do see a consistency though, and we would like to analyze this, summarize this in some meaningful way without having to just pick out individual cereals. So here's where PCA really shines for examples that are much bigger than this. Now, without getting into everything, all of the mathematics involved here, again, we are going to be using the standardized variables. So what does this mean? What do we mean by standardized? Well, we mean it's going to have not only going to be centered data, right? So we think about our data cluster maybe starting off over here, and we shift that so that, relatively speaking, it shifts to the origin. But then also what we do is we what's the word I'm looking for here? Divide by the standard deviation of that particular variable, right? So what we do is we center and we make the variance equal to 1. Okay, so basically that ensures that we're not seeing a lot more spread in one direction, because of course you can see there's going to be a big wide range of calories, right? We range all the way from, let's see, what's the lowest? Around 140 all the way up to 210. So you can see that data is naturally going to have a higher spread in calories from, let's say, 140 to about 210. But you can see sugar doesn't, sugar's on a much smaller scale. So we have sugar ranging from 4 to about 13, 4 to about 14. Right, so naturally that range is much smaller than this range, and if we were not to divide by the standard deviation, then what would end up happening is sugar would just naturally display a much smaller principal component, and we want to consider sugar in relation to itself, right? So that's why we're going to do the standardized variable. So we're basically going to focus on the correlation of x, which, remember, is what we called z earlier. Okay, so what's the result here? Well, we see that these are the eigenvalues for that standardized matrix. Principal component 1 is by far the largest eigenvalue. In fact, if you take 4.1757 and divide it by the sum of all the eigenvalues, that's 83.51% of the total. And so you can see that most of the variability that we're observing in the data is going to be in the direction of PC1, with a little, roughly 1/8 of that is in the direction of PC2. And then really PC3, PC4, PC5 are kind of negligible, because notice we've already accounted for 95% of the variance. You might take into account PC3, but again, what we're trying to do is reduce the data dimensionally, and we see that PC1 and PC2 by far dominate the other ones. We can see that in the scree plot as well. Remember, this is just the principal component. Ignore the half steps here. We have PC1, PC2, PC3, 5, and you can see that this one, PC1, is the highest eigenvalue. And remember, we always arrange them in order of descending magnitude, so regardless of the SIGN sign of them, we just want to organize them from largest absolute value to smallest absolute value. And so you can see by the time you get to PC3, 4, 5, those are hovering there near 0. Okay, so now let's get at the actual principal components, the eigenvectors. And so remember, these are just the eigenvectors, and I just wanted to produce them in this table so that you can see the components much more clearly and what they relate to. So again, we're kind of just thinking, we're not going to focus so much on those, though we could interpret them. Now I'm going to investigate PC1 and say, all right, this vector points in some direction. So imagine that we have our space. I'm just going to draw this as two-dimensional space just for the reference. And we might see that, principal component 1 maybe points in this direction. So what does that actually mean if PC1 looks like that? Well, according to the components, now this is a 5-dimensional problem, so we can't actually visualize it. I'm just representing it kind of as an analogy in R1, right? So this is a direction, and this is where the maximal spread occurs in. And in that direction of maximal variance, what causes the serials to vary in that direction? Well, if I start to look at the loadings, okay, sometimes the principal components, PC components, the actual values inside of here, are called the loadings. And the loadings just mean how much weight is in that particular variable direction. So you can see they're all pretty closely weighted. Protein's a little bit higher, but now we're getting petty if we just say, hey, 0.48, that's bigger than 0.41. They're all pretty much close, right? And so what I want to focus on is a comparison. There's a contrast happening here. Notice that calories, fiber, protein, and sodium are all about equally negative loaded. So those are all negatively loaded, whereas sugar is positively loaded. So all that means is that we're looking at a direction that contrasts cereals with high calories, fiber, protein, sodium. And when they do have higher ranks on calories, fiber, protein, and sodium, they are going to have really low sugar, right? Or opposite of that, we could say as a cereal has more sugar, it is typically going to be lower in calories, fiber, protein, and sodium. Now that might seem kind of weird to talk about calories. You might say, well, wouldn't that be higher calories? We'll come back to that. But let's kind of give an interpretation. I decided to type this out to really kind of pin it down as closely as I would word it, right? So that's the hard part, is interpreting these, but you want to look at positives and negatives, and always think about that as some sort of contrast. As the negatives become more negative, the positive becomes more positive. So as you tend to decrease calories, fiber, protein, and sodium, you're going to tend to increase sugar. Or you could say that as you decrease sugar, you'll tend to find a cereal that is higher in calories, fiber, protein, and sodium. This is not every cereal. This is just a description, a summary of those cereals. So about equally loaded across the variables. We noticed that with the magnitudes of the values being close. It seems to be a comparison of high sugar cereals in comparison to cereals high in protein, sodium, fiber, and calories. We might think of this principal component as relating to the healthiness of the cereal. As sugar content increases in cereal, it seems like important nutrients decrease. Okay, so that's what we're seeing. That's a beautiful summary of the data, right? Kind of what we would expect. Let's go back up and say, as cereals get higher in sugar. Well, look at this. Cinnamon Swirl, highest in sugar, one of the lower ones in calories, really low in fiber, low in protein compared to some cereals, and lower in sodium. Now, sodium is probably not something that we would consider to be a healthy, thing going up higher, but we do notice that that's what our data is comparing, right? Look at the lowest sugar cereal, like Protein O's. We can see that those are a little bit higher in calories. They are higher in fiber. They are higher in protein. They are higher in sodium than a cereal such as Cinnamon Swirls, which is lower in calories, lower in fiber, lower in protein, and lower in sodium. So it's just summarizing the data that we have. And that is a beautiful component of principal component analysis, in that it takes a lot of data and really summarizes it into pieces based upon where we see the most change occurring, the most variability. Now PC2, let's investigate that. Again, let's kind of take this approach of, let's look at the loadings and the magnitude of the loadings. So first of all, I see I have 0.5, 0.6, 0.2, negative 0.2, negative 0.1, 0.5. Now, protein is really low in terms of these, so the protein is kind of negligible. I'm not saying it's non-existent, I'm just saying it's kind of negligible, but it seems to be more of a contrast in cereals that are higher in sodium, sugar, and calories. As those tend to go up, then fiber tends to drop a little bit. And so I might say something like low loading on protein. Okay, probably negligible in comparison to the other components. We might say that calorie-rich cereals with higher sugar content and sodium tend to lead to a lower fiber cereal. Okay, well, let's check that out. So if we take something like let's see what we say, calorie-rich cereals with higher sugar content and sodium, well, we can see that fiber tends to go down, right? Lots of sugar. Yeah, and we can kind of go through and justify that one by one, but the beauty is we don't need to. Now, if you're like, well, that's not totally true, it doesn't seem like that's a consistent with looking at the data, we also have to remember that's a subtlety. This guy is a little more subtle. Why is it a bit more subtle? Well, because we have to also take into account the results of the scree plot, i.e. the comparison of the eigenvalues to the other eigenvalues. PC1 is far superior to PC2, right? The only reason we considered them is because up until including PC2, we're getting the majority of our variance, 95%. But PC2 in relation to PC1, if you look at that, it is PC1 has an eigenvalue that is, almost roughly, I'd just say roughly 8 times bigger than PC2's eigenvalue. And so as a result, we would expect the interpretation of PC2 to be a bit more subtle, right? There isn't as much variability in that direction as there is in the first. In fact, we have 83% of the variability in the direction of PC1 and only about 11%. I'm not rounding properly here, but you get the idea, in the direction of PC2. Okay, so now a question we might have, and we'll answer this in the next video, is how do we somehow get a bit more of a visual representation? Now that we have this summarized in terms of PC1 and PC2, wouldn't it be great if we could come up with some sort of two-dimensional plot that compares the cereals in terms of where they fall on PC1 and where they fall on PC2? And that's exactly what we'll do next.